morning, everyone. I'm Brian Chung from Salle College, currently studying in MIT in Cambridge MA. And today I'm going to present you my project, Curve Optimization Problem. First of all, let me start with an imagined scenario. A telephone company once buried a straight cable in the underground and then put a marker on the ground right above it so as to indicate its position. But unfortunately, due to some errors, it's within 1 meter from the cable, but not quite exact. So here's the question. What is the shortest trench need to be dug in order to find the cable? And the trench can, of course, be a circle with radius 1 meter, since it's always within 1 meter from the marker, right? But the length would be 2 pi, which is 6 point something, which is quite a long distance. So to improve it, we can open the circle a little, and then the length would become pi plus 2, which is 5 point something. So this 1 meter shorter, which is pretty much improvement. So no matter what, the trench should have the key property that it has to touch every tangent line of the circle so that it can cover all the possibility that the cable may be. And so we can rephrase our initial question, which is, what's the shortest path that intersects every tangent line of a circle? And Faber, a mathematician, in 1984 showed that it's equivalent to ask, what is the shortest path with convex hull that completely covers a circle? And for this will lead to our main concern of my report. What's the optimal curve of a circle? You may ask, what is the optimal curve? So now let me give you a definition. It is the shortest path such that its convex hull completely covers a given convex set S. And our goal today is to find the optimal curve for each given convex set S. It can be rectangle or circle or ellipse. So let's see some example of optimal curves. For the circle case, it would be an inverted U shape with length 0.818 times the perimeter. Whereas for the square case, we can find that it should be 3 of its sides, and the length would be 0.75 times the perimeter. Just do some arithmetic, and we can get these results. So we can see that the ratio of the optimal curve and also perimeter depend on only the shape, but not like how large or how small that convex set S is actually. So we can define the ratio of R, and then we can ask the question, what is the maximum of R among all these kind of many convex sets? And the answer today, I'll tell you that is 1/2 plus 1 over pi, which is the case when S is a circle, as we see just now. Before I proceed to my proof, I would like to give you some terminology that I'll use quite frequently in my report. The supporting line L is a line that actually touches the shape, while the width D will be the distance between two supporting lines that are in the L direction. You can see a more precise and rigorous definition on my report. And the definition of the yurt is a little bit more subtle and is defined by construction. Given the convex set S and the supporting line L, we first draw two perpendicular supporting lines, and then by using the two intersection points, we draw a path that completely covers the convex set S. In this way, the red line would be the yurt that we want. And we first deal with a case when S is centrosymmetric. Theorem 2.1 in my report shows that the length of the yurt is always equal to half the perimeter plus the width in L direction. This is quite intuitive if you see the picture. And with this theorem, we formulate the second theorem, which is the minimum among all the yurts will be less than or equal to 1/2 plus 1 over pi times the perimeter by using some geometric inequality, and you can also see the proof in the report. And we notice that yurt, as by my definition, is actually always in gamma S, which means that its convex hull always covers this convex set S. And so we have the corollary that the ratio is always less than or equal to 1/2 plus 1 over pi. So we have dealt with the case when S is centrosymmetric. But how about the general case? In general, we first start with some observations. Given a convex set S, the length of the optimal curve will be not greater than the minimum among all the yurts, since all the yurts will be in the gamma S. And this, in particular, will be less than 2 of the chosen yurts, and the minimum of these two. And so we can actually choose the yurts. And the way I choose it would be the L0 and L0 prime are two parallel supporting lines, such that they correspond to the minimum width of S. And this quantity will be less than, of course, the average of these two quantities. And thus, we can see geometrically, this is actually equal to half of the perimeter plus the two minimum widths. And so if this one is not greater than our upper bound, then we are done. So it suffices to prove that this quantity is not greater than P over pi, which can be proved in theorem 2.2 for the central symmetric shape. But for a general case, I have to introduce you a concept, which is the Minkowski sum. The Minkowski sum, as you can see, is defined as two convex sets A and B in the complex plane, such that it's the set of all the summands of one point from A and one point from B, and then we take the whole set, and we can prove that it is actually another convex set. Moreover, it's a property that the width and perimeter can also simply add up, even though it's not trivial basically from the definition. And these are all we need to prove this beautiful inequality. So now let's just prove this last inequality. Given the convex set S, we first rotate it by 180 degrees with respect to an arbitrary point O on the plane. And then we add them up using the Minkowski sum. We can get M, which is central symmetric and also convex as proved in my report. And since the parameter of M is 2 times P, and also the minimum width of M is also 2 times the minimum width of S, as shown due to the two properties that I've just shown you. So the inequality minimum width not greater than P over pi in M will imply the same inequality in S, except it's just dividing by 2, and that's it. So we're done. We've solved that when S is circle, the optimal curve is the maximum. But is circle the only equality case? The answer is fortunately yes. And it's because the circle is the only shape that satisfies all the equality case among all those inequalities, namely having constant width and being central symmetric. So let's get back to the search of the optimal curve. We first ask us a problem. What is the shortest path such that its convex set is exactly a given convex set S? And even for this problem, it's so complicated and that we don't think that there is deterministic theorem that can include all the cases. Even so, we can tackle the case when S is just the n-sided polygons. And it turns out that the path is restricted by 3 lemma. The first two mainly tell us that the path actually passes through all the vertices of the n-sided polygon once and exactly once. While the third one tells us that the path does not cross itself. And these 3 lemmata restrict the possibilities to finitely many. From the first two, we can show that the number of possible paths will be n factorial, while the third one reduced it to 2 to the n. This is because when the k point is determined, the k plus 1 has only 2 possibilities, namely the consecutive point, or it can go to another consecutive point that is consecutive to a visited point. And it is because if we go to any other point, if we further go to this direction, it has to cross this thick red line in order to meet this red point. And the same will happen to another direction. So by contradiction, we can show that there are only 2 possibilities. So by arguing further inductively, we can show that all the visited points have to be consecutive after each move. And so a recursion can be set up, and also by using some dynamic programming techniques, an algorithm with order n squared can be written. And this indeed helps a lot in making conjectures for the original problem. For example, I initially conjectured that the pentagon case in the green line may be shorter than the blue line. But eventually, I realized that the green line is 17.11, but the blue line will be 17.16. So we can show that the optimal curve for this pentagon is indeed the green line. So the search of optimal curves is in general hard, and even for a simple case is quite tedious. So an alternative way is to give a necessary condition. And based on some observation, is when the shape is not too thin, the optimal curve would be a yurt shape, which is great. And I conjecture the following, which is the width along two perpendicular directions of a given set if this width is bounded by 1 over m and m, where m is some kind of real number that we have to search for all supporting line L, then this optimal curve is yurt-shaped. And this inequality indeed is just telling us it's not too thin. And so this is quite a strong statement since they can solve all the regular polygons for not too great m. Yeah, so here are some references, and this is the end of my presentation. Thank you.